So in the dual nature discussion that we discussed in the previous video, we had two types of calculations, one based on the particle nature of light as indicated by the photoelectric effect, and the second one is by the wave properties of the electron as indicated by de Broglie's formula. So let's do one example of calculation based on the photoelectric effect. If we have cesium metal with the work function of this value right here, and we want to calculate what is the minimum frequency of light that could eject an electron from the surface of this metal. That value here is the work function W. And according to the photoelectric effect equation, the energy of the photon, H nu node, with the minimum threshold that is able to eject the electron from the surface of the metal, has to equal the binding energy or the work function of that metal. So it has to equal the value of W. So all what we need is use the value of the work function here to find the corresponding frequency that would provide the same amount of energy to eject the electron from the surface. So we just rearrange this equation to solve for new node, the threshold frequency. So new node is going to equal the work function divided by H. So it's going to equal 3.42 times 10 to negative 19 joule divided by 6.626 times 10 to negative 34 joule second. And you can clearly see that joules will cancel with joules and you will be left with second minus 1 as a unit for the number that you will get in this case, which is going to be 5.16 times 10 to the power 14 second minus 1 or hertz. This is the minimum frequency of light that is able to eject the electron from the surface of a cesium metal. The second part of the question asks to calculate the kinetic energy of the ejected electron if you use light with that frequency instead. You clearly see that the frequency provided in that second photon of light is much larger than the binding energy. So it's going to be able to provide enough energy to overcome the binding energy or the work function and provide some energy as a kinetic energy for the ejected electron. So the energy of the used photon in this time, according to Planck's formula, is going to equal h nu. This is going to equal the sum of the work function plus kinetic energy. So if we want to calculate kinetic energy, we just rearrange this equation to solve for kinetic energy. So kinetic energy is going to equal energy of the photon used minus the work function. So it's going to equal 6.626 times 10 to negative 34 joule second times the frequency, which is 1.00 times 10 to the power 15 second minus 1 minus the work function that is given right here, which is 3.42 times 10 to negative 19 joule. Just remember that that product here, second, is going to cancel out with second minus 1, and you will be left with energy in joules that you can subtract from that energy in joules of the work function. So it's going to equal 6.626 times 10 to negative 19 joules minus 3.42 times 10 to negative 19 joules, which is going to equal 3.2 times 10 to negative 19 joules. This here is going to be the value of kinetic energy that the ejected electron is going to gain in this case. And we can actually do the calculation based on this equation on the other way around. Like if you know the kinetic energy and the work function, you can calculate the energy of the photon used and vice versa. We also discussed the wave properties of the electron as given by de Broglie's wavelengths. So let's calculate de Broglie's wavelengths for the electron when it moves at a speed of 68 meter per second. De Broglie wavelengths for the moving electron is given by this equation right here. Lambda equals h, which is Planck's constant, divided by m, which is the mass, times v, which is the velocity. So it's going to equal 6.63 times 10 to negative 34 kilogram meter square per second. This is an alternative unit for Planck's constant using the dimension analysis for joule to equal kilogram meter square. And we divide this by the mass of the electron, which is given right here, to equal 9.1094 times 10 to negative 31 kilogram, multiplied by the velocity, which is 68 meter per second. Just to make sure that this calculation is set up correctly, let's see if the units are going to cancel out. So kilogram is going to cancel out with kilogram. That meter here is going to cancel out with the square. And the second is going to cancel out with second. And you will be left with meter, which is the expected unit for wavelengths, which is going to equal 1.07 times 10 to negative 5 meter. So let's repeat this calculation for the electron if it actually moves at a higher speed instead. So instead of 68 meter per second, let's increase the speed to 9.38 times 10 to the power 6 meter per second. And let's see how the characteristic wavelengths of this electron is going to change. As we said, characteristic wavelengths is going to be given by Planck's constant divided by the mass times velocity. So it equals 6.63 times 10 to negative 34 kilogram meter square per second divided by the mass, which is 9.1094 times 10 to negative 31 kilogram times the speed. The new speed now is 9.38 times 10 to the power 6 meter per second. And as usual, just to check, we can see that kilogram will cancel out with kilogram. Meter is going to cancel out with the square. Second is going to cancel out with second. And you will get a number in meter, which is expected for the wavelengths. That is going to equal 7.759 times 10 to negative 11 meter. Just to put this into perspective, the new wavelengths here in comparison to the wavelengths when the electron was much slower that we calculated in the previous slide, which was 1 times 10 to negative 5. So when it was slow, it has a frequency of 1.07 times 10 to negative 5 meter. When we increase the speed significantly, we see that we made the associated wavelengths, the characteristic wavelengths, much shorter. And how this helps in electron microscopy is that in order to be able to see anything or picture anything, the wavelength you're using has to be smaller than the size of your object. In case of optical microscopes, we're using visible light, and visible light usually has wavelengths that is larger than 400 nanometer, which means using the optical microscope will allow you to see objects larger than 400 nanometer. Anything smaller than 400 nanometer is not going to be visible. Now, if you look at that wavelengths for the beam of electrons, you see that this is actually equal to 0.77 angstroms, which is smaller than the typical size of the smallest atom, which is usually on the scale of 1 angstrom. Meaning that using this wavelengths, you should be able to visualize any object down to the size of a single atom.